This is a continuation of example 3b, in which I will explain now in detail how to use the residual to find the partial fractions of this complicated expression into these three parts. Let's copy the equation we had. So it's y over z, yz over z. This is, on the left is hz over z, on the right is xz. Now we have the numerator of z and the denominator of z. All these are in positive powers of z. To get the numerator of z, I'm going to use we are multiplying these coefficients. Actually, we can also use the word convolution to multiply two polynomials. So this is the trick here. The numerator is 1 convolving with z squared minus z cosine 0.03 pi. So this power is z squared. This guy is power 1, and therefore we need to put a 0 here because this is z to the power 0, 0 to the power 1, 0 to the power 2 for the numerator as NUM. The denominator, we're convolving z minus 0.95, so the coefficient is 1 for z and minus 0.95 for z to the power 0. Convolving with z squared, so the first coefficient is 1, the second coefficient is minus 2 times cosine 0.03 pi, and the last coefficient is 1. So the numerator and denominator are gotten this way. So what we have now is y of z equals to the numerator divided by the denominator as factors. We don't even want to see these values immediately. We can send y of z into, we can send the numerator and denominator using the residual to find RPK. And RPK shows us this is R1, this is R2, this is R3, and this is P1, this is P2, and this is P3. You must remember that I'm using positive powers of z, and that is why I'm using residual. Let's do the easiest one first, which is P3, because P3 is not complex conjugate, so it is just a single pole. So it goes to here. The pole position is 0.95, so z minus 0.95. The corresponding R3 is minus 3.9593, so it's here. So we always look at R3 and put it on top, and the P3 with 0 minus whatever this value is. Now look at R1 and R2. They are complex conjugate of each other. The poles are also complex conjugate of each other. So this is not an accident. We are interested in the pole position that has the positive imaginary part. So look, this is real part and positive imaginary on top, real part and negative imaginary. We are interested, let's focus on this guy, this pair. So we put the pole here. So pole is 0.9956, so of course it's z minus 0.9956. This is positive, it got minus. Okay, so don't get yourself confused, because this is z equals to, then we have the whole negative values of this. So it's 0.9956 plus 0.094. Correspondingly, we'll put this value here as well as this value here. Alright, then we can focus on this rational function, and then we can manipulate it so to become a polar representation, and then after that we can extract all these four values out and put it into our cosine, as I have explained. Now in the next figure, I will show you the plotting of the transient, which is this equation. So it is R3 minus 3.959 times the pole 0.95 to the power of n. What about the steady state? Y5 steady state is 2 times R1. What is R1? R1 is 4.782. What is P1? P1 is 0.0942, which is 0.03 pi. And then we have a delay R1 again, which is minus 1.0257. I plot the steady state and the transient as well as the sum. Okay, let's see the figure next page. The steady state is a cosine of 0.03 pi and its amplitude is 2 times 4.782, so it's almost up to about 9.5 values here. So the steady state of a cosine looks like this, and it's phase shifted because see, at time origin it is not sitting at the peak, is not at this location but shifted, delayed. Now what about the transient? The transient starts from -4 and after a while it just dies. So when the steady state plus the transient, when the transient dies, then the cosine is it looks like a cosine that is phase shifted now. But in the front, you realize that the steady state plus transient is not what you expected of a steady state cosine. Now, to be absolutely sure that I didn't get it wrong, I write the difference equation and I send my x into the system and I simulate the difference equation here, and I also can plot y3, which is plotted as the green x. So you realize that the green x is the same as the red, and the red is the sum of the steady state and transient. So this is a very nice example. Please try it in the lab as well. Thank you.